4K's private tuition. So this is a continuation of yesterday's lesson where we were talking about Leclerc's principle, where we introduced the concept of equilibria. Now let's talk about what would happen if you tampered with the temperature in the reaction that we were looking at yesterday. So the reaction was that of hydrogen and nitrogen to give us NH3. So in this reaction here, the forward reaction is a negative enthalpy change, meaning that it's exothermic. So the forward reaction is exothermic, which implies that the backward reaction is endothermic. So what would happen in this case if we increase the temperature? The equilibrium will shift to try to reduce the temperature. So how does this happen? How can we try to reduce temperature? We do so by triggering on the endothermic reaction. Why? Because the endothermic reaction requires heat, therefore it will use up the heat. So when you increase temperature by adding more heat, the system is going to reduce the heat by carrying on this endothermic reaction, in this case, which is the backward reaction. So an increase in temperature will promote the backward reaction, will result in the formation of more hydrogen and nitrogen, which in the other terminology that we learned yesterday, we would say the equilibrium would shift to the left. So it's important for you to be able to make this kind of analysis. So if we increase temperature here, the equilibrium will shift to the endothermic direction. This will reduce the temperature and more nitrogen and hydrogen will be produced. So you must be able to also summarize this. What happens if we decrease the temperature? So if we decrease the temperature, the equilibrium will shift to the exothermic direction. This will increase the temperature. So you see that here your system is always opposing what you're doing. When you decrease your temperature, it will increase the temperature. When you increase the temperature, it will decrease the temperature. So this is what we said here according to Leclerc's principle. The equilibrium will move to counteract the change. So a decrease in temperature will shift to the exothermic direction, which will result in the formation of more NH3. So this is important for you to take note for temperature. Now let's talk about catalysts. So you need to understand that of the factors that we described so far, changes in condition that we were talking about, we talked about pressure, we talked about concentration, and we were talking about temperature in this case. You can also use a catalyst, but catalysts have no effect on the position of equilibrium. They have no effect on the position of equilibrium. A catalyst will only speed up the rate of the forward and backward reactions equally. So what it does simply facilitates for us to achieve dynamic equilibrium faster and not necessarily affecting the position of the equilibrium, whether it's going to be shifting to the left or to the right. Catalyst has no effect on that. Let's talk about Kc, the equilibrium constant. Now this Kc is for homogeneous systems where your reactants and products are in the same physical state. When you have different states, then those reactants or products that are in a different phase or state are not going to appear in your Kc for in your expression for Kc. Okay, so let's talk about this. Kc expression can be worked out from the molar concentration in a reaction. So we'll look at the concentrations of the reactants and products. So a generic equation is before here, A plus B to give 2C, 2A plus B to give 2C and D. The molar values in front of each species, which we call coefficients, become the powers in the Kc expression. So if you were to write a Kc expression for this reaction, you would say, here you can see you have products here, C and D, over reactants, but you have C raised to the power of 2 because the coefficient of C is 2, and you have D here raised to the power of 1 because the coefficient would be 1. A to the power of 2 because you have 2 here, and B to the power of 1. So assuming A, B, C, and D are in the same physical state, so this is for homogeneous system. systems. Okay, let's go to look at an example here. So write the Kc expression of the following reaction. Here is sulfur dioxide plus oxygen with sulfur trioxide. So it's already balanced. You can see the coefficients there. So this is take note here of the physical states here. All the species here are in gaseous phase. So this is a homogeneous reaction. All reactants and products are in the same state. So all reactants and products are included in the final Kc expression. So let's look at this Kc expression. So we have our products here, which is sulfur trioxide raised to the power of 2 here because we have a 2 here, over your concentration of oxygen times concentration of sulfur dioxide raised to the power of 2, because for sulfur dioxide here the coefficient is 2. So this is the Kc expression, and sometimes you're going to come across questions that require you to just write this expression for Kc. So you must be able to create the Kc expression. Let's look at this situation here. We have a situation here. The Kc expression can be worked out. We talked about the molar values in front of each species are powers in the Kc expression. The molar values in front of each species are powers in the Kc expression. We talked about this. Now, I want you to look at the physical states here. We have gas, solid, gas, gas. So this one is a heterogeneous system. So in a heterogeneous system, solids are not going to appear in your final Kc expression. So you remove solids. You also remove pure liquids such as water. So a pure liquid or a solid are not going to appear. So you can see here your products are C and D raised to the corresponding powers 1 here, and A to the power of 1, but we do not see B in the Kc expression because this one now is heterogeneous and solids are not supposed to appear. Okay, so take note of that. Write the Kc expression for this equation here. You can see here, take note of this. So it's always important for you to check the states. So solid, gas, gas. So the Kc expression is not going to include this solid here. So this would be the Kc expression in your product, CO2 raised to the power of 1, O2 raised to the power of 1. And we do not see any carbon there because solids are not going to appear. Okay, so let's look at a specific example where we have to substitute the actual molar the concentrations. So write Kc for the expression and calculate the value of Kc of the following reaction. Sulfur dioxide here is 0.4 moles per cubic decimeter, here is 0.2 moles per cubic decimeter, and 0.8 for the sulfur trioxide. So remember your Kc expression. What it's supposed to look like here. You have your product raised here to the power of 2, divided by your oxygen multiplied by your sulfur dioxide squared here. So let's just substitute the numbers there. 0.8 here for our sulfur trioxide squared, and our 0.2 and 0.4 squared. So our Kc is going to be equal to 20. And it's important here to take note that you are supposed to also calculate the units. So remember, you're dealing with moles per cubic decimeter, which are your concentration. So here it's concentration squared, so moles per cubic decimeter times moles per cubic decimeter. Here it's your concentration, which is moles per cubic decimeter, times your concentration squared, moles per cubic decimeter, and moles per cubic decimeter. So we cancel out here these two on top with these two at the bottom, and we're left with 1 over moles per cubic decimeter. And we have to invert now. And we get our moles to the power -1. So the 1 here inverts to a -1, and the minus 3 here to a +3. So this is how we calculate our units. We have to cancel out in the numerator and denominator as shown here. So this would be our units, and units are going to differ. As you can see, they are affected by these powers here. Okay, let's proceed to talk about Kc when you are given some background information here. Let's look at this. Nitrogen dioxide decomposes according to this reaction: 2NO2 to give 2NO and plus O2. So we are told here that 33.2 grams of nitrogen dioxide were heated in a vessel with a volume of 9.65 cubic decimeter at 450 degrees Celsius, and 6.88 grams of oxygen were found in the equilibrium mixture calculate the value of Kc. So we heated this and we found this amount of oxygen at the end in this reaction vessel. So now we need to create a table like this. Okay, so you need to remember initial concentration, change, and equilibrium concentration. Here rather we are dealing with moles. So initial moles, change in moles, and equilibrium moles. So let's look at this. So remember the acronym ICE, initial, change, and equilibrium moles. So let's plug in the information that we know here. We know that we have 33.2 grams of nitrogen dioxide. So we can calculate the number of moles that we begin with here. So mass over MR, 33.2 divided by the MR of your nitrogen dioxide, 14, and 16 by 2 for the oxygen. So we have 0.72 moles here, 0.72 moles. And remember, this is the initial moles. So at the start, we didn't have any of the products, so 0 for your nitrogen monoxide and oxygen. Now we are told that at the end we had 6.88 grams of oxygen. So we can calculate the number of moles there. Mass over MR, 6.88 divided by 16 by 2, we get 0.215. So we had 0.215 moles of oxygen, which is the change here. We had 0 and now we have this 0.215 at the end. So our equilibrium moles is going to be this plus this to get 0.215. So for the products we are adding new moles. For the reactants we are subtracting. So just remember that. So we can now use the molar ratios. We can now use the molar ratios to work out if this is the change that we had, how many moles of nitrogen monoxide were also produced here, and how many moles of nitrogen dioxide were used in order for us to get 0.215. So you can use your molar ratios. So here it's 1:2. So we have 2 times this amount for the nitrogen monoxide. So that would be plus 0.430. Remember, we are adding here onto this 0. We are adding this. So the final would be 0. In the final row here, we would have 0.430. Here we need to understand that we are subtracting. So the ratio is the same. 1 here as to 2, so we'll get the same amount here, 0.430. So remember, it's a negative because we are subtracting from the initial moles. So we would get here, if we subtract, we would get 0.29. So our table is now full. Now remember our Kc expression, we need to now calculate the concentrations. So we are given here that we had a 9.65 cubic decimeter container. So we can change our moles to concentrations. So we would have here for the nitrogen monoxide 0.045 if we divide by the 9.65, which is the volume. Oxygen 0.022. Nitrogen dioxide would have 0.030 moles per cubic decimeter. However, there's another method where you can just plug in the moles. If you know for sure that all these species were in the same sealed reaction vessel, then you can just plug in the moles directly into the Kc expression and you would still get the same answer. So if we write our expression for Kc correctly here and substitute here and evaluate, we would end up with a Kc of 0.050. For the units, we have to calculate as before, cancel out there, and we'll be left with moles per cubic decimeter. So this is how you would calculate Kc given this background information. So we are going to look at now a situation where you are given Kc and you are asked to work backwards from Kc to find the equilibrium concentrations, but we'll do this in the next lessons. So just remember that on Friday we're going to look at past examination questions that involve Kc, and we'll proceed from there. So I'll see you tomorrow. Go through this material. You can also ask any questions and we'll interact in the group.